Hello, Graham. Welcome back.
Hi, Emiliano. Thanks for having me back in.
Okay, today I would like to go back to an issue we discussed a few months ago now, and when we discussed Russell's response to Zeno's argument and his enthusiastic adoption of Weierstrass's understanding of limit, and we said that Russell claimed in the principles that by banishing all infinitesimals, Weierstrass has at last shown that we live in an unchanging world, and the arrow is truly at rest at each instant during the motion. And you and I agree with you, objected to this understanding, the emerging understanding of motion, the at theory of motion, on the ground that it deprives instantaneous velocity of its intrinsicality. So instantaneous velocity is no longer an intrinsic feature of the object, and this seems to conflict with the explanatory role that instantaneous velocity should play. Now, Russell's comment on the consequence of the rigorization of calculus, the arithmetization of calculus that we discussed last time, seems to imply that to locate the difficulty in Zeno's argument and his request that things can only change by being changing. That is, that if we are realist about change at all, we must be realist about the gerundive, so to speak. So, and also by connecting the banishment of infinitesimals with Zeno's difficulty, he seemed to think that Zeno was right when he thought that instantaneous states of motion are inconsistent, and that this inconsistency is precisely the inconsistency of the notion of infinitesimal as it was introduced when calculus was invented and ridiculed by Berkeley, and that finally, getting rid of infinitesimals in favor of limits explained what was wrong with Zeno's argument. Now, in the 60s, Abraham Robinson showed that there are models of analysis that are consistent and that comprise infinitesimal as well as infinite numbers. And can you give us a gist of this result and what these structures look like?
Look, I think your summary of the situation is completely accurate. Okay. So there are at least three things on the table here. The first is non-standard analysis. The second is what one might say about infinitesimals in the light of that. Actually, there are four things in play. Another is Zeno's argument. And the fourth, lurking in the wings somewhere, is paraconsistency and its relevance to this. Okay, so those are all interesting thoughts. Let's start at the beginning with the non-standard analysis. So the Robinson construction is a fantastic, it's a very beautiful model theoretic construction. And what the Robinson construction shows is that if you take the standard classical theory of the real numbers, the continuum, then this of course has a kind of standard model, which is, the standard mathematical real line. But like most theories, it's going to have non-standard models for technical reasons concerning logic. And what Robinson discovered was that some of these non-standard models have rather fascinating properties because they contain things which appear to behave very much like infinitesimals behave in the traditional fashion. So, for example, there can be things which are kind of these things. Let's call them infinitesimals in this technical sense. They can be closer to just take 0 as a fixed point, right, which is real. But the same consideration is going to apply to any real number. But fix on 0, then there are going to be these strange numbers in these models, which can be closer to 0 than any real number. So closer than a quarter, closer than an eighth, closer than the 16th, and yet non-zero. So in that way, they behave very much like what one would think traditional infinitesimals behaved. There's one way in which they don't behave, in which traditional infinitesimals behave, and that is they're consistent, because you're dealing with sort of classical model theory, right? So what Robinson showed was that there is a certain way of consistentizing the classical theory of infinitesimals. By classical, I mean sort of Newton, Leibniz, Bernoulli, etc., where you can have things which behave very much like traditional infinitesimals in a consistent fashion. And moreover, if you try to do calculus in one of these non-standard models, then a lot of the old intuitions which pump the infinitesimal calculus actually go over very, very smoothly. So, for example, the intuitive notion behind continuity is that a function is continuous if, when you get a continuous at a point x, if when you get infinitely close, arbitrary close, no, if you get infinitely close to x, the function, the value of the function f, gets infinitely close to the value of fx. Okay, so this is sort of a continuity argument. Now, if you look at the way that calculus is done in the Cauchy, Weierstrass, Dedekind way, that's the definition of continuity is much, much more complex, because it involves sort of, for every x there is a delta, etc., etc. So it's much less intuitive in a sense. Whereas if you can do your calculus in one of these non-standard models, you go back to very much like the old intuitions. You can say that when you're infinitely close to x, then the value of f of x is also, the value of f there is infinitely close to the value of fx. So the reasoning becomes very intuitive. It's one of the beauty of the subjects. So that's fascinating. It shows that in a certain sense, the old reasoning can be inhabited or instantiated or realized consistently. There are limits on what you can do, though, of course. First of all, these new models, in a sense, don't give you anything new, because it turns out that if you take the old theory and the language it's expressed in, then you don't change anything. Anything you could express in the old language as true in the standard interpretation is going to be true in the non-standard interpretation as well. In technical terms, they're elementary equivalent. So you don't sort of disturb anything that you had before. And in a sense, that's good, because it shows that you don't have to reject the old theory. It's just this kind of different way you can conceptualize it, and a very natural way. There's a kind of hard issue about whether or not one should actually take the continuum to be not the real line, but one of the kind of non-standard real lines in one of these non-standard models. That's something that people have played with, and that's an interesting issue. But I think the orthodox feeling amongst mathematicians about this is that really the real line is all you need. And these other things are kind of interesting mathematically, but just because the non-standard construction is, in a sense, equivalent to the standard construction, you don't really need it. That's the first issue.
Okay, but the possibility to construe of motion as in terms of instantaneous infinitesimal advancements seem to go in a direction that Zeno was after. After all, you can be a realist about the gerundive if you understand instantaneous velocity as the ratio of two infinitesimals, and effectively this means that during a timelet, an infinitesimal timelet, the arrow advanced by an infinitesimal amount. And in a sense, I mean, we discussed your view of motion with the idea that objects in motion are spread out inconsistently in different positions, and there seems to be some kind of similarity between the two ideas. And of course, in your case, that is inconsistent. In this case, it would be consistent.
Yeah.
But do you think that the idea of an infinitesimal advancement comes close to answering the need for an explanation? In your way of expressing the paradox, you say, how can the arrow go anywhere by not going anywhere at even an infinite number of times? But in this case, it seems you might be able to say that the arrow is actually going somewhere in a little timelet.
Sure. That's a natural thought. I think it's not the case, but let me try to explain why. You're right about the original infinitesimal calculus. The thought was that these could make sense of the notion of instantaneous velocity, and therefore maybe go some way towards solving Zeno's paradox of the arrow. And it does this by allowing that the point of the arrow or whatever makes progress in its motion in an instant. Okay. Now, with the kind of epsilon delta analysis, that goes out of the window because, as you said in your original summary, at any point in the motion, the arrow does make absolutely zero advance because the point of the arrow is exactly where it is and nowhere else. Okay. When you throw in the Robinson infinitesimals, that situation doesn't actually change, precisely because you're dealing with a consistent situation. So even though there are lots more of these points, these infinitesimal points, as well as the standard points, exactly the same is true of those. So if you look at the location of the point of the arrow at one of these points infinitely close to zero, let's say, it is exactly where it is and nowhere else, because the system is, the theory is consistent, okay? So, I mean, if you found the original situation with respect to Zeno's paradox problematic, with the epsilon delta calculus, you're going to have exactly the same problem with respect to the infinitesimal calculus. Adding in the infinitesimals is nice, it does some things that are nice, but it doesn't get, but exactly the same story that was problematic in the case of the standard reals is going to arise with respect to the infinitesimals. So in that sense, I don't think it helps to address that particular problem.
You mentioned several times in your writings the fact that mathematicians and scientists accepted a notion that was blatantly inconsistent shows that we can actually rationally accept inconsistencies. But strangely, you never mentioned infinitesimals as an example of possible dialetheism. I mean, last time we talked about inconsistent arithmetics, and I was wondering if there exists something like inconsistent calculus, if you see what I mean.
Sure. Okay, two things. First of all, there's a sense in which mathematics in the 19th century got rid of infinitesimals, and I'm happy to go along with that. I don't feel the need for postulating infinitesimals. I'm happy with the standard real line. In certain ways, it's going to behave inconsistently. And it's there that the solution, I think, to the physical problem of Zeno's arrow lies. So I don't want to bring back infinitesimals. Oh, I've got nothing against infinitesimals as mathematical structures. They're beautiful, right? But in terms of applying it to sort of physical motion, I'm quite happy with the real line and inconsistentizing it. Okay. So that's why I've never invoked infinitesimals as a plausible case of dialetheism. Okay. Now the second thing is a bit more complicated. That is that it seems pretty clear that in the Newton-Leibniz tradition, which lasted 200 years, mathematicians did work with inconsistent objects, infinitesimals. I mean, they were quite content to assume that an infinitesimal was non-zero at one point in their computations and zero at another point. Okay, and they recognize this. I think that's fair to say. Of course, they weren't logicians, and even if they had known about logic, well, Leibniz was a logician, okay, but the mathematics of the day wasn't, the logic of the day wasn't up to theorizing how this was possible. They just did it like most mathematicians do, kind of, naturally. So there is a question of how you actually understand what was going on mathematically and logically in what they do. Now, one natural thought is you just take what they were doing and you impose on it, or I take it to impose on a paraconsistent logic. So you just take infinitesimals to be inconsistent objects and carry on. Now that way really doesn't seem to work, because sooner or later you're going to find yourself dividing by zero. And if you divide by zero mathematically, all hell breaks loose. And there's nothing in paraconsistency which will stop that, okay? So simply taking the calculus to be done on the basis of an underlying standard paraconsistent logic doesn't seem to work, okay? What does work is something like this. And this is a mechanism that I've written about with an old friend of mine, Bryson Brown, called chunk and permeate. You really do seem to need to break the computation of derivatives and integrals up into chunks. This is, often our reasoning is chunked in this way. That's certainly true. So you have one chunk where you reason as though the infinitesimal was non-zero, and then you have another chunk where you reason as though it's not. Okay, that's the chunking. However, of course, these chunks have got to cooperate in some sense. So some kind of information flow must be allowed between the chunks. So you do the chunk where you assume that the infinitesimal is non-zero, and then you allow some information to percolate into the chunk where it's zero, and then you carry on the computation. Now, one cannot allow everything you deduce in the one chunk to percolate into the other, otherwise you're back with the original situation where you're just working a paraconsistent logic and all hell breaks loose. So there must be some constraint, some filter on what is allowed to permeate between one chunk and the other. So we call this structure chunk and permeate. So you break up the computation of chunks, and you have something which allows a certain amount of information to permeate from one chunk into the other. And if you do it that way, things seem to work out very well. There's probably not much point in going into the technical details here, but that's the idea. And for my own part, I think that really what was going on in these in the early days of reasoning about infinitesimals up to about the 19th century really was this chunk and permeate structure. You don't need infinitesimals, you just need things which behave in contradictory ways in different chunks.